Welcome to our lesson 1.7, which we're going to be talking about transformations of functions. In our last lesson, we talked about different parent functions. In this lesson, we're going to talk about utilizing those parent functions to graph other functions that are related to them. And first, we're going to talk about different shifts of graphs. So we can have vertical and horizontal shifts to a graph. We say we're going to let C be a positive real number, vertical and horizontal shifts in the graph of y equals f of x, where f of x is our parent function, are represented as follows. 1. We have a vertical shift C units up if our new function, which we'll call h, is equal to the parent function plus c. We'll have a vertical shift C units down if our new function h is equal to the parent function f minus c. We'll have our horizontal shift C units to the right if our new function h is equal to f of x minus c. And finally, we'll have a horizontal shift C units to the left if our new function h is equal to f of x plus c. Which that probably does not make a whole lot of sense, but let's take a look at an example and see what that really means. So we're going to look at example 1, where we're going to look at using the graph of f of x equals x cubed, so it's a cubic function, to graph two newer functions. So f of x is going to be our parent function. The first graph we're going to look at, we'll call this A, is going to be g of x, which is going to equal x cubed minus 1. We're going to graph our parent function, f of x equals x cubed, in gray, and then we'll change up the color when we're graphing g of x. So f of x equals x cubed. If we're going to graph that when x is 0, 0 cubed is 0, so we can put a dot at the origin. 1 cubed is 1, 2 cubed is 8, so we're going to put a dot at 2, 8, which on my screen goes too far up. It's going to be off the screen. So we'll start moving into the negatives. Negative 1 cubed is negative 1. Negative 2 cubed is negative 2, which is not negative 2. It's going to be negative 8, which is also off my screen. So if we're going to connect these dots to roughly represent our cubic function, our function would look like this. This minus 1 here at the end of g of x, that tells us each point in f of x is going to be shifted downward 1 unit. So all we're going to do is take each of these points and move them down 1. That's all we need to do. In fact, in this case, that's going to even bring our 2, 8 onto our screen. So now we can connect them, and we're going to have our g of x function graphed. So here in blue we've got g of x. In gray we have our f of x. Let's also look at another function, still utilizing the original parent function, f of x equals x cubed, but this time we're going to have h of x, and it's going to equal the quantity x plus 2 cubed, and then we're going to add 1 to that. So from our original points in f of x, what's going to happen? We're going to use red. This plus 2, that tells us we have a horizontal shift 2 units to the left, and the plus 1 tells us we have a vertical shift 1 unit up. So each of our original dots from f of x, we're going to move 2 to the left and 1 up. 2 to the left and 1 up. Which also means we'll get our lower bound back in. So we can connect those, and we can get a rough sketch of h of x here in red. So we utilized the ideas of those horizontal and vertical shifts to sketch graphs from our parent function. Another type of transformation we're going to look at are reflections, so reflecting graphs. All reflections in the coordinate axes mean is reflections in the coordinate axes of the graph of y equals f of x, our parent function, are represented as follows. Number 1, a reflection in the x-axis is represented by our new function h is equal to the opposite of our parent function. So if we take and multiply everything by a negative, we'll get a reflection across the x. A reflection in the y-axis is going to mean if we have our new function h, it's going to be equal to f of negative x. So again, maybe a little bit confusing, but let's look at what that means. We're going to look at example 2. We're calling this reflections and shifts. We're going to compare our parent function f of x equals the square root of x to a couple reflections. So our first one we're going to look at, we'll call A, is going to be g of x is equal to the negative square root of x. First, I'm going to take a minute and graph my parent function. The square root of 0 is 0, square root of 1 is 1, the square root of 2, I don't know that exactly, same with 3, but I do know the square root of 4 is 2, and I'm going to call that good. Here's my parent function, f of x, in gray. We'll use blue to represent our reflection, g of x. Since g of x is just the opposite of f of x, this minus out in front of the parent function tells me all I'm doing is I'm going to take the opposite of each y value. So at 0, I'm still going to be 0, but now when x is 1, my y is going to be negative 1. And at x is 4, my y is now going to become negative 2. This is a reflection across the x-axis. Let's look at another one, b. We'll call this one h of x, and it's going to be equal to the square root of negative x. Now this one's kind of strange, but it's not much different. It still is utilizing our parent function, but this time the negative is inside the parent function. So what that means is we're going to be reflecting not across our x-axis, we're going to reflect across our y-axis, which means 0 is going to stay 0. In fact, all that's really changing is we're making our x negative but keeping the original y. So now we're going to, instead of going negative 1, 1, instead of 1, 1, we're going to go negative 1, 1. Instead of 4, 2, we're going to go negative 4, 2. So this red graph represents our h of x. And I forgot to use my blue to label our g of x. In fact, let's now take what we've learned in this example and the last example so far and do one more. We'll call this one k of x. And we're going to set that equal to the negative square root of x plus 2. We're going to take a reflection and a shift. So we're going to do this one in green. And what this negative here tells me is first I'm going to take each point and reflect it across my x-axis. And then this plus 2 tells me I'm going to have a horizontal shift to the left 2 units. So first we're going to take our point, reflect it, so 0, 0 is still going to be there, but then we're going to move that 2 to the left. At 1, 1, we're going to first reflect it and then move it 2 to the left. So 1, 1 becomes negative 1, negative 1. We're going to do the same thing with 4, 2. 4, 2, we first reflect it to 4, negative 2, and then we move it left 2. So our new point becomes 2, negative 2. Once we've done that, we can connect our points, draw our arrow, and call this k of x. Alright, let's move on. These next type of transformations are my least favorite, but I still need to teach them to you. These are non-rigid transformations. We were just talking about rigid ones, which really just means we're moving them. This non-rigid thing, essentially what we're doing is we're looking at vertical stretches and vertical shrinking, as well as horizontal stretching and shrinking. So vertical stretches and vertical shrinking both kind of go off the same idea. If we say f of x is our parent function, then g of x is the new one. It's equal to c times f of x. And if it's a stretch or a shrink, depends on the value of c. So if we have a stretch, that means c is going to be greater than 1. If we have a shrink, that means c is between 0 and 1. So if it's a stretch, it just means we have a c value that's bigger than 1. Shrinking means we're going to have some c value that's a fraction or a decimal. With horizontal stretches and shrinks, we're still going to say we have g of x as our new function, but it's going to be equal to f of c times x, where c is still some value we're going to be multiplying by. But again, this is stretches and shrinks differ a little bit here. If we have a stretch, that means instead of c being bigger than 1, we're going to actually say c is between 0 and 1. Whereas if we are shrinking horizontally, that means c is going to be greater than 1. Again, something that's kind of confusing, but let's look at an example to see what these vertical and horizontal stretches and shrinking, which in some textbooks, the shrink is also called a compression. Let's see what those look like. So we've got example 4. We're going to have our parent function be f of x is equal to the absolute value of x. And our first function that we're going to look at is going to be h of x is going to be 3 times the absolute value of x. So here in gray, I'm going to graph my parent function. The absolute value of x, if we put 0 in that, 0 is 0 units from 0. 1 and negative 1 are both 1 unit from 0. In fact, if you remember how absolute values work, all this graph is going to look like is a v. So our parent function, f of x, here in gray. Let's use a blue for our h of x. And all h of x means is we're going to take each of our original y values and we're going to, our x values, and we're going to multiply them by 3 once we've done the absolute value. So we're still going to be at 0, 0. But now if we take the absolute value of 1 and multiply it by 3, we're going to have a new point at 1, 3. 2, we're going to have a point at 2, 6. Negative 1, we're also going to have a point at 3, and negative 2 also at 6. So this 3 that was outside of our absolute value, this was a vertical stretch. What we did is essentially we took and pulled up. If we were to hold on to this function, we pulled it up. We do have a b, but I'm running a little short on time with this video, so we'll catch b in our next one.